So, last time we spoke about differentiation and how that might help in terms of uh, computing optimization for some of our algorithms. But today will be a little different, given that, as you know, everything in terms of large language models, as well as what's going on in terms of the development of making sure that these models have some sort of reasoning all encompassing so that they're able to almost emulate a human being in terms of vision and also of a thinking. And so what we'll be talking here today is that how those vision language models are almost like computed in terms of their embeddings, their tokenization, not only from a text perspective, but also from a visual and image perspective. So let me start here. Um, and so as you can see here, there's a few things that we've looked at in terms of image processing as well as object detection. And the first thing that you would probably see is making sure that you're able to detect that this is a red truck. It's surrounded by trees. And, here you have a red truck. It's parked. Oh, sorry, can't see. It's parked on a street lined with trees, right? And so you would have a caption for each one of these images. Um, And there's another way that you could consider an image and text is this aspect of visual question answering. So this is trying to capture the spatial answers that you could get from an image. So is this truck considered vintage, or does the road look new? It doesn't really look new other than behind, or what kind of tree is behind the truck? And those are two types of image captioning that I want you to think about while we go into uh, our our lecture. And so I don't know if anybody has taken a digital image processing course. Has anybody taken a course on image processing? No? Yes? Uh, you can put in the chat. It's okay. Many have to taken image processing course. Okay. So in the same way that you would have, oh, sorry. Text. The same is true for image. You have position characteristics, you have edge detection, you have in different intensities, right? If you're depending on the type of image. So all of this is just uh, an image in lieu of to a matrix. And the same is true for if you're trying to think about a vision language model or LLM per se. Now, in the context of colored images, they're considered tensors because they're multiple matrices together. And so you have a channel and you also have the height and width. And those, again, this is even more so in terms of the magnitude of those matrices, right? So many times when you're trying to detect some of the edges, you're trying to detect maybe a face or different characteristics or texture features, you would have a filter, which is in itself another matrix, in order to get what you're trying to delineate. For instance, for edge, many times you have these types of, again, from the differentiation point of view, Sobel filter, you would have a canny detection, all these things that would come into with the image in order to get an output image to detect those edges, right? So if you think about these large language models or vision language models, you're really trying to get an image input as well as a text input, right? And to do a certain task, whether or not is this aspect of image captioning or trying to figure out spatial differences within that image. Who has ever used maybe ChatGPT or Claude from Anthropic, or maybe some of these open source models such as Kimi, as well as anything on Olam, to be honest. Any thoughts? Yes? No? Maybe?
That's
Um,
GPT, yes.
okay. And so depending on what you're trying to ask, it will answer based on with its text, or you will have maybe to generate an image, or you will give an image in order to ask a few questions about the image. Now, whether or not it's actually correct in terms of interpretation, that's a different story. But you always have some data domain, whether it be text, image, it could be voice, it could be a video in itself, all for it to compound to get and do a task. So when you're thinking about these large language models, these are specialized models for these different tasks, whether it be to output, again, text or a combination of both image and text. So many times what you'll do is, oh, sorry. Many times what you'll do is that you can pre-train a model that acts as foundation with lots and lots and lots of data. So again, large scale data set, like many have people done in terms of OpenAI. And then you would have this foundation model enabling some of these high throughput tasks, whether it be in terms of fine tuning or a zero shot, and you can use it in terms of maybe clustering different types of patterns, or if you can give it context, and you can probably give it more of a few shot approach. And so many times what you'll do is you'll have language. You could be in terms of a corpus, and you will train, and then you'll have GPT. And in order to get some of these tasks in terms of math problems, symbolic reasoning, trivia, or any type of translation from maybe one language to another. And so there are different classes of foundation models. So you have language such as Almo, BERT, GPT. You have classification. So depending on a set of features from an image, or you could try and figure out how different patterns, different features within an image will maybe be used for diagnostics. In this case, in language model, as in terms of vision, there's some in the medical image space where Flamingo, for instance, has used X-ray images and some of its denotations from radiology reports. And they would output, again, based on the training, some of those aspects of what you would see from a physician standpoint. Again, it hasn't been completely accurate, as otherwise you would probably see it much more in the healthcare system. But, if you think about it, you're all encompassing this aspect of more of machine intelligence in terms of language and vision. And now, if you think about more other task-based approaches, SAM or segment anything, we use that a lot for, again, segmentation of different organs, depending on a CT or an MR. And again, if you have the opportunity, you can probably see that it's open source. So all these things can be done and further done through this large amount of data that's inputted for training. And this aspect of visual programming is a little bit interesting because, many times what these models fail at, unfortunately, is this aspect of visual spatial context. So if I can present it with an X-ray of maybe a lung, it can probably say that there is some sort of little nodule or some other nodule or an aspect of an abnormality. But if you were to give it context in terms of where is maybe the pleura, or where is there space where there's low resolution, it probably won't be able to tell you, just because that visual programming context is not there. But these are the different categories. And so what today will be leaning more on is, yes, this aspect of classification on a term, but even more so in terms of language and vision. How do you get these tokens or these embeddings from a language as well as vision, and how do you concatenate them, or how do you combine them in such a way that you're able to make any type of task viable? In terms of the medical context, how can you see a radiology image and really truly detect some of the abnormalities there from a SAM. Right now, I'm in a COPD meeting, so maybe in the context of an imaging from the lungs, that could tell you a little bit more in terms of, okay, the vessels are atrophied or they're very they're coming into each other, as in they're small in terms of their volume in that specific generation. And so that could also tell you context about a disease. So to do and to understand this, you have to always see foundation models as being able to do multiple tasks. It's not just a classification task, it's so much more than that. And what you'll have is, you have large numbers of parameters, large amounts of data, and there's always this self-supervised training, pre-training objective. No one is just going to be training data that's not imputed with some sort of expert level oversight. So, you have to really think about some of these foundational models. I mean, I know Momo has a small foundation model that was actually open source, but some of these foundational models are very data hungry. And not only data hungry, but also computation hungry, compute resource hungry. So many times I've had conversations with some clinicians that will say, I have maybe 2,000 CT images of maybe of the brain, and I have these annotations or delineations of a hemorrhage. And so I can actually do a foundational model based on TBI or traumatic brain injury, just based on this data. No, you need just much more context than that in terms of a foundational model. Not just in terms of just 2,000 images just doesn't cut it. It has to be all encompassing. So that's why I'm inviting you to think about these foundational models of being able to do multiple tasks. And so many times what you'll do is, I mean, if you have some sort of classification problem, in this case, you can think about trying to delineate a batch number of images from a cat, from a monkey, or maybe a dog, and you will extract some features depending on how they look like, and you will try and train a small classifier, and from there get the classification of the respective animal, right? And so the main ideas here is that you're trying to learn or train based on without any labels. So maybe what you'll do is you'll augment the image itself, and by augmenting, you're truly making it bigger. And you would have the original image with this augmented version. You would push those areas together, and then if you augment another image of the dog in this case, and then you would push those things apart just for the self-supervised pre-training objective. Oh. And so this aspect, if you were putting more context in terms of making that differentiation from a cat and dog standpoint, you just would put more data about it, different types of things, because you as an individual, you as a human being, could tell that actually, this drawing of a cat is an actual cat. And then the cat that's in different colors in terms of black and brown with its green eyes, that's also a cat. But many times as you know, some of these models have been kind of siloed in the training data. So you have to really learn these representations in order to have this generalization of what you need from a foundational model standpoint. And again, this is specific to just the images. Now, I'm going to invite the floor. How would you be able to bring more context into classification of a cat and a dog? I'm going to call you guys to be more interactive because I'm going to be looking at the screen and I'm not going to be giving just the answers. I want you to really understand because this will give way for the next parts of the lecture. You can unmute yourself. Okay. Manny, do you want to say something? Because you're the only person I'm seeing.
So you are asking about general representation of maybe
Yeah.
a cat from a dog.
What would you need to ha know context? If I was to just use your senses, your just think about your senses as a human being, what are different things that you would need to know whether or not this is a cat or dog? If I was to say meow, you would have
Mhm.
this as the context of that cat, right?
Yeah.
What about what's something else that you could probably get from a data standpoint?
So I mean, visually, looking at the difference between the features of a dog and then a cat, I can see that the ears of cats, they are kind of somehow erect or
Hmm.
upright, small, I mean, kind of upright. But dogs, some do have large ears, and then yeah.
Yeah, so you're trying to build that context. What I'm trying to get at here is you can also generalize beyond images, right? That's why I said meow on the terms of a cat or a woof, I guess, in terms of a dog. You know, these are also voice inputs, right? And so in the ca case of a vision language model, in terms of generalizability, you really need that aspect of image, but also text. So this is a very cute, fluffy cat, or this is my favorite dog is a golden retriever. You know, you are inputting some information from the text, and then again binding them with some of that information from the image. Um, so this is what where vision language models comes in. So
Excuse me. So it's like you're telling the language model that, let's say, dogs bark, cats meow.
yeah,
So
that
you're
could be a
you're
sentence
training
itself.
it. Yeah, so you're training it on what are the differences.
Yes, and probabilities within their we'll talk about that there, but probabilities on how it's being placed in. So if you're saying cat meows, like the cat meows to the dog or things of that nature, that also allows for that generalizability in order to distinguish between the cat and the dog. But you would have features that are specific only to cats. So for instance, the image itself, as you see, on top of that sentence, this is a fluffy cat.
Well, that would be confusing, wouldn't it? Because also some dogs are fluffy. And in terms of like size, cats are smaller than dogs, but
Yeah,
there are also some dogs that are the same size as cats.
yes. But you would add to more sentences. And we'll talk about attention, this aspect of attention within these models that makes this not so nuanced, as in not so difficult. I mean, not so difficult to distinguish. So keep and you're actually asking good questions about this, but yes, you will have context not only in terms of the images, but also the text.
Excuse me.
Mm.
Yes,
Are you referring to something that the the trademark that only cat has, but dog do not? So if it is this the thing you're asking, then I would say the fur of the pattern. Like you see that on the cat, it was kind of like um, I think the cat has its own pattern of the fur.
yes. So
Like
when you're
not the same as the dog. The dog will you will see generate different patterns.
Yes, but that's why I'm telling you not to focus so much on the specifics, but more of a data input standpoint, right? When you're trying to train something, just to just do a classification of a cat and dog, um, for your training, you're really going to put those labels of this is a cat or this is cat with a maybe a binary uh number. So it could be zero, the cat could be zero, and then dog is one. And you're trying to really distinguish between the classes, right? And you would have all these images from the cats and all these images of the dog, and then you would parse them such that you would train your model to just get those features, maybe some of those edges are specific to cats or certain texture features are only specific to cats to actually allow that for that to test whether or not your model is able to distinguish between a cat and a dog. What I'm trying to bring here is not necessarily, okay, the dog is very fluffy, the cat is very fluffy also, but there are two types of inputs or two types of data inputs such as an image as well as a text, that can help you distinguish that even further, given a foundational model with large and large amounts of data. Does that make sense?
Yes.
Yeah. Okay. So to really go into this, we have to talk about tokenization. Has anybody heard about tokenization before? I mean, with this whole, have you ever looked at,
Yes.
yes? Who has said yes? Manny.
Yes.
Okay.
It came from the large language models, right?
Yeah,
Yeah.
so
Yeah,
this,
I've taken that too.
oh, you're taking, oh, okay. You're taking the class with Sandeep?
No, we took it last summer, me and Joe.
Yeah.
Okay. Okay, great. Well, then you guys are experts.
No.
So, so what I'm trying to say here is, so this aspect of tokenization for people who don't know is that you're really converting strings, in this case, like words, and the sequences of maybe integers into different tokens or different IDs. So if you were to take this, you would encode, and this is where you would impute the data. You would encode them to have these different IDs or positional IDs as to how, sorry, you would get those positional IDs to the original sentence. And what you do is you'll decode those IDs to make sure that when you're able to break up those strings into their respective segments. So if you were to put Stanford was founding in 1885, there's different ways that you can build that corpus. Sorry, different this is the corpus. Different ways you can build the identification. And this is, you're putting an ID depending whether or not on a word specifically, or it could be, in this case, Stanford. Those are two different IDs. So that's the encoding portion. And then you would, even the space in this sentence has an identification or an ID. So these are, if you think about it, almost like a mini barcode for the sentence. The same is true if you were trying to take it in terms of an image, right? Each one of, if you were to build this up into different patches or different areas within the image, you can pull and encode them into these different codes or these different barcodes. So if I was to split this up, and I would turn the matrix of this image, I could, each one of the portions within those splits, give them those barcodes IDs. And then based on those barcodes IDs, I could represent this similar image from what I started in the beginning. Because that context or probability between those barcodes, how similar they are together in terms of making sure they're predicting the next barcode is true in order to get the same image. Does that make sense?
Yes.
Okay. Has anybody seen this paper? I mean, you guys went to looked at attention, right? This idea of large language models or even visual language models have the same basis. This idea is based on the tokenization or the embeddings from not only the words that you're getting from a sentence standpoint, but also from the visual standpoint. But the attention or the way that you're trying to get those probabilities of the next word or even the next patch image embedding is specific to this idea of single-headed self-attention. And this is what you would get from a transformer. The transformer is one of the biggest things that is being used in terms of for these large language models as well as VLMs. So we're going to go through self-headed self-attention, a little bit of multi-head self-attention, and a little bit of cross-attention, because the idea of tokenization, of just having the decoder and encoder from a text standpoint, is still true from an image standpoint. And that the concatenation between the training data from the image embeddings are just going to be what gives out your output for this visual language model. So if I was to put, just for context, an image of a cat, and I would patch it up into its embedding visual embeddings, and I would have a sentence that says, the cat is the cat is running the field. That on itself, those two things will give those concatenated features embeddings will help to determine, once I train the data with monitoring amounts of data, the aspect of if I was to put a picture of a cat, I should just put a picture of a cat. The model should be able to tell me that this is a cat running on a field. Does that make sense? Okay.
Yeah, giving an image input, is the text kind of the supervised input
Mm. For the training,
for the training?
yes.
Okay,
Joel
okay.
or Jun?
Yeah. Excuse me, can you tell us what is the number 56 represent in previous slide? Can
Uh,
you give us
No,
yeah,
so
I
we'll
see a
talk
lot
about
of
that. We'll talk
yeah,
about that, but you're trying,
okay.
it's just it's like I said, it's a mini barcode because these are matrices, right? It's not only a position, it's not only looking at the position of where these patches are, but also the context or the visual features that maybe you could get from um just for regular image classification. So this could be edge features or anything else, or maybe the 50th or 90th percentile, any radiomic features really. Uh, and then so this barcode is specific to maybe a patch of that image.
Okay.
Just the same way that each word in a sentence could be a barcode, the same is true could be for an image. Does that make
Okay.
sense?
Okay. Thank you.
We'll
Excuse
look
me. So
into
you're
it.
saying that this whole barcode might not represent the entire image, but just a part of the image.
Yes.
Okay.
But the way how they relate to each other, as how one barcode relates to each other, is still the same. Or the way that
Mhm.
you think about attention is still the same from an image, from a text standpoint. Because it's just a probability of how well or similar they would be together in the
Mhm.
contents of the image. Hence why when you're looking at the decoder, you're being able to get that image back.
Um, can I ask one more question?
Mm-hmm.
Yeah, because previously in the text-based data, we use tokenization that is predefined. Like
You have
each word
corpus. Yeah.
is assigned to a specific number, and it's already being conducted by others. And I wonder, is that the same thing in the image tokenization that you need a predefined, pre-created data to assign each, I don't know, maybe pixels into a specific number to encode that,
It's
to
not
encode it to tokenization. Yeah.
so predefine is a strong word, to be honest, because you would, as you know, for tokenization, even for words, in terms of language, the way that you tokenize is also very different, right? You could have different types of tokenization and still have different outputs based on the training,
Yes.
right? And
Yeah.
so, predefine in this context is yes or no, just based on the way that you're trying to build those features from a visual standpoint as well as the text. So like I said, if I was to have a chest CT of a lung and I was to put in the lung that says this lung has 5 lobes, the way that I would get those barcodes in terms of visual and then text will be very different depending on the tokenization that I have. And so we'll talk about that, but the reason why I'm thinking about tokenization here is that it's relevant for vision language models. You really have to fuse together that spatial context from a visual standpoint with some of these words that are coming in from a language standpoint. So we'll look into that, but I'll go forward. So just going to go over single-headed self-attention. I think this is important because just because visual context or visual features are being inputted. Oh, is there? Oh yeah, you put in the chat, sorry. Okay. So just the way that you think about language in terms of probabilistic getting to the next word, you're also doing the same thing for that vision programming. Right now, it's not as if you can do that for diffusion models, being able to create images based on context of your language. But in the vision language model spaces, basically you would have an image and you're able to output a language form or the text form in order to describe that image. So yes, you're training based on both image and text, but really when you're doing an output, you're just testing based on that language output as well. Does that make sense? So it's not bidirectional in nature, not truly. But in terms of attention, I really wanted to go over this in terms of how you compute these different aspects of attention for trying to get the probability of the next word through this aspect of key linear neural networks, getting the query value, getting the query, and then the value matrix from just these input embeddings that you would get from the image or the text. So if you were to have an example that says, let's say the input of our attention block is a sentence, I have to go. I have to go. The word is being identified with a number or barcoded with a number, and you would have that as your embedding vector. And the same way that we were thinking about those pixels within an image, you have to think about it also in this context of language. So it's a little similar in terms of both areas. And I'm doing this because a lot of people might not know what's going on in terms of that attention block for these large language models. So you convert every single word into a number, this barcode, and then in itself, that would be the embedding vector within your model. So I have to go, you'll have a barcode of 342, 879, 438, and then 342. And each one of these will have a vector, being an embedding vector for your model. So what you'll do is again, you're turning this whole sentence into a matrix based on that barcode or based on that embedding vector. And so this is the same is true that if I was to say I have to go, or I said the cat is white, the cat is white would have 3 words. So it'd be a 3x3 matrix. Oh no, it's 4 words. The cat is white. So it would be a 4x3 matrix again. So each one will be representing that single word. And so every row in the matrix corresponds to every word. So this row will be 1 word, this is another, and again, going downstream the same. And so in this aspect of finding that K, Q, and V values, those are in itself different matrices. And again, I'm bringing this up because not only large language models do this when you're training, the same is true for these visual embeddings. So the way that you do this is you get these trying to derive some of these query, key, and value matrices in order to get this aspect of attention, this attention matrix, in order to really know how the next word is going to be, or really how that next image patch will be also. Does that make sense? Nod yes? Okay, so this is the actual formula for attention. You have softmax, which is what will give you in terms of probabilities. And then you have these 2 matrices in terms of transpose matrix of K, the Q, and then also the value matrix as well. But these are all specific to, again, that simple sentence, I have to go. So just wanted to bring forward here is that DQ, or the square root of DQ, is not a matrix, it's an embedding dimension. That embedding dimension is telling you that dimension when we looked at each one of those words has three different numbers, as you saw from the previous slide. You see these three different numbers, that's that embedding vector. So if you were to put the number here, d subscript k, the embedding vector would be 3.
Okay, I think I am missing the bigger picture here.
Okay.
So generally for supervised learning, what I've read is like you have an input and then you assign that to specific outputs, but maybe you use just the input to train your model. After that, you compare the outputs of that model to your assigned numbers, compute the cost function, and then try to minimize the error until you get the best. I mean, that is the general
Yes.
view. So in this context, I am kind of getting lost. Where does this attention
Okay,
fit in?
so yes, you still have that aspect, but you have to understand that you have more than just two labels, for instance. You
Okay.
have a whole sentence where you have to generate or output another type of sentence based on the original sentence that you've inputted. And that's
Okay.
within your corpus, this whole aspect of, depending on those barcodes I was saying before in terms of those sentences. This is not necessarily like, yes, I completely agree. You would have all this stuff. If you were just to think about these labels of, let's say, I don't know, you have normal people who have normal lungs, and then you have people who have lung cancer, right? And you would have those labels for each one. All
Mhm.
that process is true, but now I'm telling you for a foundation model, that's not enough. Because for a foundation model, you have to be able to do many, many tasks. You have to be able to have that spatial context. If you were depending on a normal classification model, you would not be able to really ask uh, this aspect of where this lung is normal is where is
Yeah,
the left lobe, right? So
yeah,
it's really
yeah,
impact. It's
yeah. I do understand that, but I am saying that I mean I am kind of missing where you insert this attention. Is it the input,
oh,
the out? Yeah, that
okay.
is
So
my
let me
question.
go
It's like I
back.
not understand.
Okay, so I think I wanted to go into the nitty-gritty of here, but let me show you another slide that I had here so you understand a little bit. Um, you can understand a little bit of where I'm coming from. So, let me share my screen. Mm, okay, so do you see the slide? Yes.
Yes.
Okay, so let me go back. Um, yeah. So every single aspect of every single aspect of a large language model has a certain architecture, right? But how well you're able to predict the next word in terms of your output, is based on this aspect of attention. How well you're able
Oh,
to really get information about an image is also a probabilistic um, component. So you have an image encoder, you have a text
mhm.
encoder, you have these barcodes for in terms if whether it's patch based or not, and you're basically concatenating those to train your model. What I'm saying is
Oh,
that
okay.
beyond that, before you do that, you have to do some matrix multiplications for those that attention layer, just so that you're able
Oh,
to
okay.
really see the context of what you're trying to label. So in this case, the dog, the cat, the monkey, those you have an image encoder, you have a text encoder, but the way that you actually put, like I said, attention are really
Mm.
true probabilities between those two, or even within these images, is specifically based on attention. Hence why we're actually
Okay.
doing all the computation almost by hand, so you really visualize what's really going on
Okay.
in the
Okay.
background. Does that make
Okay.
sense?
Yeah. Yeah.
Okay, so let me go back. Um, mm, uh, but this is a good question. I mean, yes, you have to really know the big pictures. You're trying at the end to train a model on both the text and visual embeddings. But the way that you do that, how do you really train a model and how you're actually computing that? That's where I'm going to be teaching.
Okay.
So, and so there's a lot of people who will use ChatGPT or they'll use um, um, Claude for even, code optimization, but they don't really know what's going on in the training standpoint. And this is why I bring this up because even the way that you present or you encode your text, the way that you encode your visual embeddings, or they can be different and can give
Yeah.
different results. So, but we really have to go into, the
Yeah.
computation of that. So, given a certain sentence, like I said, you're turning this into an embedding vector, with different types you have an embedding vector, and then you would have that be a whole matrix, right? A representative matrix for this sentence. And so each word will have its own row, and then from there, each row will be the embedding vector for the word. Yeah. But there's three important things that you have to think about in order to get that attention. Those similarity scores from the context of a language as well as an image. And this is aspect of attention. So the Q, K, and V are all three matrices are highly, highly important to really denote once you're trying to train and not only train your model in terms of a foundational model. Yeah. So, and then the softmax, I know you guys know this. We use this a lot for classification, but you're turning these vectors into probabilities. So once we actually have those Q and K and V matrices, you put that into the attention formula and then you get an output matrix. But has anybody done this by hand?
No.
No, right?
I
So
haven't.
we're going to be doing this literally by hand.
Okay.
So ideally, here is how do we actually get that query key and value matrices from our input matrix of I have to go, right? The X matrix is your I have to go and your input matrix, right? But you're really trying to find your key matrix. And so the way that you do that is that each one of the key as well as query and value matrices will have different set of weights, depending on how well you're doing the similarity scores. And these will have specific neural networks in order to derive those output matrices. So if I was to have an X matrix and I had, um, oh yeah, and if I had wanted to know get a head size of 2, will be the output. You would put this embedding vector, you pass it through the linear neural network, and that will produce your key matrix. And a number of output neurons. So in guess here, the head size that would be 2. So here's your input, your weights, and then you would have your output or your head size. Make sense so far?
Yes.
Okay. And so what you would do is, if I was to put these are my weights. I put that in terms of each one, this one row. You think about it, this one row is I, right? And I go and do some dot product. I would get these values of Y. So these are our weights. And then you would pass it through. So again, 0.1 times your first weight, the next one, up until you get these values of Y. And so at the end, if you were actually do this by hand, you would get y1 to be 0.34 and then 1.28 for the next one for y2. Oh, yes.
Excuse me. Is the values of W here is random generated?
Yes, randomly generated. This is just an example, right? I have a set of weights for either the query matrix as well the value matrix and then the key matrix. But we're trying to get the output matrix for the key, the query, and the key matrix. Sorry, key, query, value matrix from the end, given those linear neural networks. Does that make sense? So I know I put this as a little bit, but you have I being 0.1, 0.2, and 0.3 being that row. And given the set of weights, you would get this output values of 0.34. So if you keep on doing that, in terms of each one of those rows, just going through those weights, you'll be able to get a query matrix of this for each one of those words. Make sense so far? Yes. So before we were able to just do it for the I, but I have to go through all of that sentence. And so in this case, if you're really thinking about calculating attention in terms of plug and play, this is what you would get as your output matrix for the key. Make sense so far? Yes?
Yeah.
Okay. And so this is also true when you're trying to do the query matrix. You would still go through a linear neural network with different set of weights, of course. And you would go and pass this through to each one just to get the key matrix, the Q matrix, as well as the value matrix. And you really need that, even though the weights will be different. The matrices are going to be very important because that attention or that level of similarity that you're trying to put in for your sentence is going to be important for the output or when you're actually testing in terms of a foundational model or predicting that next word. So, so this is the embedding vector. You're going through a different set of weights, and then you would get a different query matrix. So this is actually very self-explanatory. I wrote it because, many times when you don't actually know what's going on in the back, but those matrices are going to be important, like I said, for that attention. And so once you're getting that embedding vector for each one of these words, you would have that final query matrix. The same is true with the value neural network. Those will be a different set of weights. And again, you'll have a value matrix. And so when you're really thinking about those embedding vectors, this could be a different sentence. The way that they're all imputed together will be give different probabilities as how they are within that sentence. And so this is how you would usually think about how you would get that query K and then V matrices together. And you have to consider also bias, but we're not going to be looking at that right now. And so again, this is actually very, very simple. It's just the dot product, from different matrix multiplications. But from what I understand, not a lot of people have taken, or either has been a while since they've taken linear algebra. So in this context, you would multiply Q and then have the transpose of K, which is your K matrix. And then you already know that the embedding vector size is 3. And then you would also multiply this by the value, right? So you have these 3 matrices. And so you would transpose this, right? And you would transpose the K matrix, have it to be in this manner. And then you would multiply again by the dot product from the Q matrix to the K transpose matrix. And this is just one part of your equation for attention. But this is very simple, and yet that makes it some of the biggest proponents for these transformers, right? And so, again, this is if you just think about the dot product, you're just taking the row, multiplying by the column of the next one, and then you would get a final value. Or in this case, your a more transformed portion of your embedding vector. And so if you really think about it, this is a K matrix of the I have to go. You transpose it, these are the numbers, you multiply it, and at the end you would have this, you will multiply it by the dot product, and you will have this end result of Q by K transpose equation. So this whole aspect is all based on the key and the value and the Q matrices. You're able to get how well one word attends to the previous word and then after. So to the previous word. And so if you're really thinking about it, if the entry is 0.80 in terms of the Q times K transpose matrix, 2 attends to I, and then the 441 expresses how much go attends to 2. Does that make sense?
Yep.
Yes, Joe.
Excuse me. For example, the word have and the word have in the column, right? And another word have the same word in the row. Why their score is not 1? Because they're the same word.
Well, you haven't done the probabilities yet, right? You haven't turned this into a probability
Oh,
just
okay.
yet by the softmax. So you don't have that 0 to 1 normalization.
Oh,
So you're not there yet.
okay.
Does that make sense?
Yes.
Yeah. So, you still have, that makes a good point. This is why the whole self-attention, if you really think about um, oh, if you really think about have, you have some of those words have different types or levels or different numbers for this whole matrix. But you're not there, like I said. Okay.
So would it be 1? Because that would mean that
No, you're
it
doing
wouldn't be
the
1, right?
multiplication, right? You're doing the multiplication from the matrix multiplication from that query matrix and the K transpose. You won't have a whole one just based on the dot
Yeah, it
product.
wouldn't be a whole 1.
No,
But
it won't. It
from
won't.
what I remember isn't it like the or sorry, it's like the probability of this word coming after. So wouldn't it be
You
so wouldn't it
haven't,
have more of a correlation with another word that would come after it rather than have again?
yes, but you haven't done the softmax function yet.
Okay.
Right now, we're just getting the query, and then you're multiplying by the K transpose or the key transpose matrix. So if you really think about the attention, you haven't really gone to that softmax portion yet.
Okay.
You're just doing this.
Okay.
So you have the Q times the K transpose matrix, and then you divide it by the embedding vector size. In this case, is 3, or length, sorry. And so this is, you would input again through matrix multiplication into the softmax function. And this is a function for softmax. So if you think about a matrix Z, a 3, 4, and 6, you would have these numbers imputed into the softmax equation, and in itself would transform it into this softmax matrix at the end. And that's where you would have that 0 to 1 aspect. Does that make sense? So from there, you would have the Q by K transpose. You would input that into the softmax function. And like I said, you've seen before, this is how it is. You didn't put those values there. And then at the end, you would have these probabilities. Have you ever seen it in this context before? Like very nitty-gritty?
No.
No.
No. And yet this is so simple. So this is in terms of numerical methods. I know this is discussed, but you really have to think about what's actually going in the background. And so that's how you would have these three matrices, and then you would have it go through the softmax function as well, and then you have those probabilities as to how they attend to each other. So in the end, you would have a matrix attention matrix looking like this, right? These will turn these aspects of these probabilities, and then for instance, I is attendant to I, have to go, and so each one of those probabilities will be seen there. So I attends to I, have attends to have, to, and then again I attends to go. But this is again, you're really thinking about the words, how they relate to each other in the same sentence. So that's the self-attention portion. Does that make sense? Yes.
It's good. So after applying the softmax, take for example the second column and the second row, it should be the same word like half, right? But why just see 0.18, which is kind of very low compared to 42. Why
Uh,
why
where do you
why
see
the word itself is not highly correlated to itself?
0.18? Where do you see it? Like 1.18? Oh, 0.18.
Yeah, the
Okay, so
second
I
column and the
have,
second row.
So you have, I mean, this was it should be, technically should be, but I put different numbers for the initial matrix, right? So the way that when you actually do that in terms of its multiplication, it will probably be more closer to 1 once it's actually the softmax. But you're right.
Okay.
So I have to go. I have to go. Go should actually be higher. So I understand.
So the value in the diagonal axis should be the highest among the row
Yes.
stack.
And so from the operation that has been made, um, I see the softmax output to be kind of the kind of weighted probability of how each word attends to the other, right?
Yes.
Yeah, so each row kind of sum up to 1.
Uh,
Yeah, from this computation. I mean, before multiplying by v, it appears kind of each row um, kind of
it would just be a
sum.
probability towards the other word, but it won't always be necessarily 1 just
One.
because you
Okay,
have a corpus, right? So it won't
okay.
always be. Um, but in the end, again, this is mainly for you to think about, you have these different matrices. There is an actual attention output matrix that you have to get. Oh, Joe, do you have a question? Sorry.
Oh, no. I'll lower hand. Sorry.
And so this is what would go and be done in the background, given if you really think about it in NumPy array. And this aspect of self-attention can be made even further if you have even more heads. In this case, like just more of that same computation within the same sentence. And so what you would have is maybe different values. And then you would be able to have these multi-head self-attention equations but going through the same process as you've done with just this one head attention or self-attention. Cross attention is different because in this case you would have, let's say you say I have to go, and then the next sentence says like Manny is at the market. You're really looking not only at that attention or similarity between the words within the same sentence, but more across a different sentence. Does that make sense?
Yeah.
And so the cross attention really thinks about you have a target and then a source. The target could be the original sentence, or it could be a different the different sentence after it. But this is just different. As opposed to having self-attention being specific to that one sentence or that specific image, you're just looking across attention from an image to image perspective or an image to text perspective, image text to text perspective from these different sentences. Does that make sense?
Yes.
Yes. So here, I don't know what type of language this is, but does anybody know? No. So you have, I have to go. They're in different languages, and like this is another aspect of a task, right? You're translating something. Yet they both mean the same. You have the same context of the text, and you're trying to put more attention, hence the multi-head, the cross attention, sorry. So they will have different embedding matrices or embedding vectors in this case from the I have to go to this other language. Does that make sense?
Yeah.
Okay. And so I put the link here, and I'll probably send it to also Dr. Ari. But this actually shows you every single step of how you're able to get within that transformer block these attention layers, these multi-head attention layers, and not only in getting the key, the query, and then the value matrices. The problem is that in this, even though it's really amazing, you're not really seeing the computation, what's happening behind the scenes. Hence why we did this mini exercise as to how you actually computing the dot product for all these matrices. Make sense?
Yeah.
So one thing that you can do is, whenever you have some time, is go to the site and really test different aspects of what you could change those probabilities at the end for given a certain embedding vector, right? So you could change the temperature. So temperature will change your results. The top K or the top P, again, will have also those explanations within the site, but those will also be affecting your results. So the reason why I put this is that I think you're all trying to do some sort of, maybe you're doing some machine learning task. You're really doing some deep learning tasks also. But if you're really thinking about using or fine-tuning some of those models that are open source, you may be able to optimize that even further, given your previous context of how it works. Does that make sense? Yes?
Yeah.
Okay. So yeah, this is a really great site. And I played around. The temperature usually has a very fixed temperature, but you can change it depending on your experimentation. By the way, Joe, did you use this in your LLM course also?
No. First time I
Yeah.
see it.
First time.
Yeah.
Okay, it's a really great resource.
Okay. Thank you.
And so if you go back to this aspects of image encoding and then text encoders, it's very similar. You would have, you really have to look at the approach from how you're trying to contextualize those embedding vectors from the on a patch basis from the image, and then also doing the same with that tokenization from the text. So here you would have like Pepper, the Aussie pup, this aspect of clip or contrastic pre-training. You would get the Pepper, the Aussie pup, you have a text encoder, and then you would try and do the same thing for the image. You would patch base, and at the end you will have a similarity score of how well the text is imputed with the image. And that's what you would use for training. So, I mean, the clip has been used a lot for medical imaging, but you would pre-train the network based on a task. Like, let's say that you're really trying to get context of, like I said, a lung image, and then you really want to know whether or not the person has COPD, right? But you're taking the reports from radiology, and you're taking also the images, and then you're trying to see how well they match to each other based on those visual embeddings and text embedding. And so, and then you would turn that into more of, but then what you do is from the pre-trained, you putting that back into the model, and then you're actually classifying. So you have these two different types of inputs. You're trying to see the similarity scores together, and then you're putting that back, whatever similarity scores, into the model. And that's what contrasting contrasted learning is in this terms of clip. Does that make sense?
Yeah.
Has anyone used clip in their architecture? No.
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 Who's my electrical and computer engineering person in here? I mean, Manny, you're one, right? Technically.
No, I'm in vision science.
But yeah, I mean, you've used a lot of clip in terms of you have to pre-train a network and do that. So if you really think about it, you would apply the image encoder just the same way that we did in terms of getting the matrix. You would do the same thing for describing that image. So this is a white and orange looking cat or something. And you would apply the tokenizer. Oh, Joe?
Excuse me. Can you talk about how we generally encode the image so we can get the embeddings of the image?
You would do it patch base. We'll go actually how
Will we talk about later
yeah, we can talk. I mean, you can talk about it now, but we can talk about it later. But if it makes it easier for everybody, I can talk about it now.
Okay.
Okay, so let me go. Let's see. So here we're gonna go here. Do you see it? Do you see my
Yes.
screen? Okay, so you're giving that image, and you would turn this into image patch medicines. How that happens is that you would cut it up, right? Depending on the size. And then that's how you get the image encoder. You would do the linear projection, see how similar they are. Sometimes you have positional embeddings because that's the way that you would see in terms of the image. And then in the end, you would have the transformer encoder, and that's when you get you put that further into the architecture.
Okay.
So here is just a little bit more. You have 16 by 16 pixel patch. You flatten it, and then you put that through a linear layer, and then you put that even further in terms of that in the embeddings into your architecture. So if you go back to this part, you're really just doing that patch-based portion really here.
So it largely depends on the pixels, right?
Yeah, it could be,
it cannot be like more than the image pixels it has.
Mm-hmm.
Okay. So the more pixel the image carries, the more accurate, the more information it is into the embeddings.
Yes. Although some people will do some pre-processing, like any type of image pre-processing. So if you really don't have the computational resources, you can downsample a lot. And that will also affect, your visual encoder,
Okay.
your image encoder. Makes sense?
Yes. Okay.
Okay. So you have, from what we saw here, once you have these patch-based embeddings, you would impute that into your model with the text that you have. As you can see here, you have the tokenizer, this is some text, you put this into the tokenizer, you have your embedding layer, and you have all this matrix that's then passed through the LLM, right? And so this is the same that is true. You have the image encoder, you have the image patch embeddings, you have the projector, which is also a little bit of a linear regression. And then you put that into, you would have your matching those spaces with the text. So this is some text and you pass this through. So you have image tokenization and then text tokenization. And yet the attention portion is still very similar if you're just looking at the image alone and then text alone. And so here, the image encoder takes a role of the tokenizer. So you have the image encoder and you're really imputing that with that text. Hence why I'm telling you that, hence why it's important that when you're really training a model, you're not necessarily doing a bidirectional aspect of those image embeddings and the text embeddings. You can have some context of the spatial information, but it will never be accurate depending on how you tokenize your text and how much you put in terms of your training. And so here you would have the image encoder, like I said, you project that in order to make sure that your text and your image dimensions are the same. And then you would impute that into your model. And so this is they look at in terms of the Fourier transformer decoder. You have these image patches. You project these into this transformer, and yet this also will have the text together. Just so you're able to parse it. Make sense? I know it's a little boring in terms of making sure that you're able to grasp the material, but when you're thinking about training a mini VLM, or maybe fine-tuning a mini VLM, you really have to have really nice descriptions of your image just to make sure that you're able to have that similarity be well placed once you're actually training, and then will be more accurate once you're testing that in terms of the outputs it actually gives. So one thing that people have done, and it's been a little bit difficult on a medical image standpoint, is that they would have the CT, like the CT image of any structure. It could be like the lung, but any structure, and trying to get information, the radiology report from the CT. And then they would have the same area, the same organ be analyzed from a PET standpoint. And so the PET is just a different imaging modality. So you have those image patching from a volumetric standpoint is very difficult. So a lot of people have been only looking at it in terms of a 2D image. But those are things to consider if you're really thinking about what type of problem you're trying to solve. The image context will be different, the text context will be different, and also the analysis or the way that it's being reported would also be different. So when you're training a model or fine-tuning a model that's already open source, and Momo is, again, open source, you just really need those really nice descriptions of your image. you have to really think about that in terms of what are the type of training data you're actually trying to impute. And so in this case, so, you have the cross-modality attention architecture. You're just really changing this GPT-like LLM. You're just really changing that attention portion, as we saw before from our computation. And so that cross-modality attention, that could be it in terms of the image and then the text. And they're just differently imputed into the model. You're just not just looking in a self-attention manner now, because you're just taking also the tokens, and you're also taking the text tokens, but you're also taking the images from a different standpoint. You're not putting this together in the same way as what you were doing in Clip. And so here, this is just a better visualization. I don't think I have much time, but this is a better visualization of what's actually happening when you have the image encoder, you have the text, you put that into an LLM in order to really get those probabilities, and then you would impute those matrices together with the image. And so that's what you would get in terms of that architecture that you saw here, in terms of the mass multi-head architecture, and then go through your actual model again. And so other architectures that have looked at it is you have self-attention, cross-attention, but there's two things that were actually placed in terms of a 2020 vision transformer. This is what it actually looks like. You would have the image encoder, feed-forward network, self-attention, and then some linear transform. Going downstream. And you're feeding forward to in order to get that representation. Like same is true that was done with in terms of the llama model. They would have the impute those different the vision transformer and also the llama model in order to get that visual representation from the image. So and then here is just like a different encoder, but you would have a speech encoder. That's when I said, the context of the cat. You could have the text, but you could also have that speech segment. And this would be the speech encoder in order to delineate what meow actually is for a cat, right? So you can have different types of data in order to have that image representation in the end. Pixtral is actually one that a lot of people have, in terms of that was published. It uses 400 million parameters in terms of the image encoder, so it was actually trained from scratch. And then this is what you would actually see in terms of trying to train the different this model in terms of the context of all these different images. And so this is just another type of architecture. It's actually kind of nice because you have this aspect of object detection. You're not only looking in terms of those patch-based embedding layers, but you also have a little bit of that object detection and a little bit more in terms of more dynamic aspect of how you're getting those patches from an image standpoint. And if you're thinking about a video, some of the biggest problems right now for video and also for a lot of people have said that the VLMs are able to predict the next image or predict the next instance after time, is that unfortunately you don't have a really nice way of incorporating the aspect of time. Even if you were to put all these different images into different instances for the image and text, just because time component is very monotonic, is very linear, forward feeding. And so many times when people have said in terms of projection is that that actually that projection doesn't really say, it doesn't actually mean that it's actually a prediction, but it could also be a past tense event. So people have looked at in terms of video, how do I know what will happen next? If I was to put in a video and in one of these models, would it be able to predict that next frame? Or what is this person doing? If I had a person that's standing alone and then someone that's just imputing in terms of the different movement for running, will it still be able to tell me that this person is actually running, given that previous discrete image of that person standing upright? And so many times when people have tried in terms of forecasting, especially in the medical image field, is that they don't do so well in that aspect. And so people have thought about positional embedding in terms of time. But I mean, this is something to think about if you're really playing around with some of these open source models, is how do you really contextualize time into these embedding layers of vision and text? But as you know, though this is based on efficiency, you really, in order to do a lot of these things, you have to consider those basics that we saw in terms of tokenization, the architecture, maybe the loss function, like you said, Manny, the optimizer, the learning rate. And even further, you have to really think about the kernels, how well you're parallelizing those your models, quantization, activation, checkpoint, inference. All these things are important because in the end, those are just going to make your task-based models much more efficient. And we are not Meta. We are not OpenAI, where we have, multiple H100s at our disposal. So we have to be a little bit smart. And by smart, I really be resource efficient in order to make this more democratized into the field. So last time we spoke about algorithm optimization in terms of making sure that you're able to do the computations with the compute that you have. But I think that we're in a good position where you're just giving the notion of these architectures, you can probably, hopefully, be able in the next few years or maybe very soon put that into perspective and training some of these models in very resource constrictive places such as, an academic institution such as UAB. So I hope this lecture was a little more telling in terms of how you go back into this aspect of vision language models, how they're actually using the embedding vectors from the images as well as the text, and how's that being computed, not only in the text standpoint, but also the images. But you have to really consider how you're able to train from scratch some of these models to do what you're actually trying to do. So Manny or Joe, I think, or Hannah also, or Sadia, depending on I know Sadia is working on some Reno work. You said, Manny, that you're working on more visual, like I think you're in neuroengineering, right? How would
Within
you,
science.
yeah, how would you use this aspect of vision and text embeddings, or for maybe not necessarily training something from scratch, but fine-tuning if you had the chance? Like, what is something that you probably use this application for?
Yeah, so I've been doing some personal reading about these neural networks, probably because I am interested in vision encoding for prosthetics.
Mm,
Yeah, but my lab's focus is about the biology side. That is our main focus. But for this prosthetic field, we first have to efficiently encode vision images to constrain by the biological limits of the neurons,
mm,
so that yeah, we can stimulate certain neurons to have this visual percept. So due to that, I have been doing some personal readings about these neural networks and then yeah, encode. So and then I kind of started some personal projects about it. So I think I will even send you an email to
yeah,
ask you questions
absolutely.
about yeah about these things. Yeah.
Yeah, I mean, I know that I went over time. I just looked at the time. But if you have a project in mind and you think that you need a little bit of help, please, you can send an email.
All
Um,
right.
this is my second time teaching. Hopefully it's good for you both, for everybody
Yeah.
here in the class. But when Dr. Ari said that, to talk about this is because I've used this aspect of vision language models in the lung space and what I'm working right now. But sometimes the nuance in terms of how it works in the background is not easily or not communicated so well in terms of the students, even
Yeah.
in some of my peers. So I think it's important to know because it's fairly simple if you really think about it. And if you're trying to make things even more efficient, you really have to think about it in terms of the architecture standpoint. So I hope this was helpful. And I'm going to send the slides to Dr. Ari. And I have a few resources from my side of what I've used in the past to use some of these pre-trained vision and language models for maybe a task of your own. I mean, I don't know if you wanted to use this for a Pokemon thing or I don't know. Those are things that you could probably use it for, or predicting the next move or something. But there are resources out there. It's just a matter of being able to have them. So the Transformer Explainer is phenomenal. I love that site because I think it goes really in a visual way and an easy way to visualize how these matrices are compounding together to get that attention layer. So thank you so much. I'm not going to keep you anymore. I think it's noon here. It's 11 over there. So I hope this was useful.
Thank
Yes,
you
it
so much,
was.
Thank you
Stephanie.
very
It
much.
was.
Thank
Thank
you so
you.
much.
Thank you.
Thank you. Send
Thank
me
you.
emails if you have. I'm
Okay.
put this in the chat. This is my email. And I'm in the Center of Lung Analytics and Imaging Research. So if you are in
Yeah.
Algen, which is the new building with a helix on it, I'm in that building. I'm in the 5th floor. Just send an email if you do. Thank you.
Thank you so
All right.
much.